We all started out as one cell big at one point. And somehow that one cell became 2 cells, became 4 cells, became heart, liver, tissue, skin cells. And somehow those cells were programmed and understood how to differentiate down all of those lines. We're using that in Epibone, and many people in our field of regenerative medicine are employing this as a technique to grow and garden tissues, so to speak. But around the time that we started developing things like interchangeable parts on the assembly line, we started to view our bodies in a similar way. If you needed a new heart, you might get one from a donor, or you might get one from a machine that was engineered in the lab. From so many different perspectives now, we're seeing that the body is being viewed as a kind of ecosystem. We can think about the immune system as a cellular system and reprogram cells from the immune system to help us fight cancer. Or in my field, regenerative medicine, we can take those cells as starting material in order to generate new body parts and organs. So our hearts give off about 1,000 times more energy than our brain. It's our largest bioelectrical organ. And what I was testing in my PhD work was whether or not those electrical signals that are endogenous to the heart, the native heart, would somehow help us engineering these tissues in the lab. This is actually a central tenet of our field of regenerative medicine. Build the environment and then the cells do all the work. So you have to do a really good job at copying the body's natural environment if you're going to coax these cells into becoming these tissues. And now we're applying a similar principle with our company Epibone to grow bone. But how do we actually grow the bones? We use digital fabrication and combine that with cells. So we machine perfect puzzle piece shaped scaffolds that we based on CT scans from patients. We infuse those with patients' cells, and after 3 weeks in a custom system patented that we call a bioreactor, that bioreactor mimics the human body. And in our case, for bones, we have to be able to really feed those tissues and give them lots of oxygen and nutrients, but also mimic the shear stresses and mechanical forces that those cells experience in the body. There are many benefits to this type of approach because there's a perfect fit. Because it's made from your own cells, there's better integration. And because it's alive, we hope that it can continue to remodel and grow along with our patients. We've published this work in Science Translational Medicine. We're really excited about moving towards clinical trials for our first product, which is a cranial bone. And we're also really excited because we've started, as Pam mentioned, growing a layer of cartilage on top of the bone. If the first industrial revolution was about machines, and the second industrial revolution is about data, isn't it exciting to think that the third industrial revolution could be about life? Thank you.